Climate change and global warming have been massive topics of conversations for decades. Now, it's a contentious subject, from people being convinced that the world is ending in the space of just years to people who think that nothing is happening at all. One thing, though, there is in agreement, and that's that on the geological scale, the Earth has always changed. And we're talking about over time spans of billions of years. And that's without human intervention. And extending from that, the world is still changing today. So the real question is actually simpler and harder. Are humans and industrial activity the main causes of climate change as we perceive it today? Now, my name is Richard and welcome to Ronc Industries, the industry blog for investors where we're pro-wealth, pro-growth and pro-industry. And today we're going to look at one of the most contentious questions facing all of us. Are we actually the drivers of climate change? And if we are, does the scale even make sense? Now, make no mistake, climate change is real. The Earth does change naturally. The key question is whether human carbon dioxide emissions are the dominant driver right now. And today, we're not doing politics. We're not even doing ideology. We're looking at the mechanisms, the scale, and also the physics. And because this is an industry channel, we're going to try to look at some of this from a business point of view as well. Now, Earth's climate has changed for billions of years without human input. Computer modeling tells us that. But at the same time, all and any computer models rely on assumptions, boundary conditions, as well as constants. Now, that's true for climate models and engineering models and finance models. The more complex the system, the faster uncertainty grows. The more certainty that we try and evaluate, the more complicated the model becomes. Weather forecasts can struggle to stay accurate beyond plus minus 2 degrees over a 24-hour period. Daily forecasts change every few hours. The longer the outlook, the less accuracy and the more updates are required until the forecast decreases and certainty increases. Now, that alone is something that everyone can relate to, and yet we're also told that we can predict decades or even centuries into the future what we can expect. Now, that disconnect really matters. The Earth is the largest, most complex system we could possibly try and model. And uncertainty grows exponentially with complexity. The Earth is not a uniform or a homogeneous mass. There are uneven distributions of land, surface covering, and geographical features that interact with air currents that interact with other air masses covering the entire globe. Waterways and oceans have different water levels and currents with different depths and salt concentrations, and these are just the variables that I can name quickly. To that end, models are tools. They're not absolute truth or guarantees. Any economist will tell you that. Now, especially at a global scale, where you're dealing with millions of interacting variables, both linear and nonlinear, the scale of the interactions to try and take into account would be simply staggering. To make models easier to work with, models are simplified. So this video isn't about trying to solve climate change, and it's not about assigning blame. It's about understanding how energy moves, as well as how it's stored. So we're going to focus on 4 things, and that's atmospheric composition, heat capacity, thermal conductivity, and heat transfer. And then we're going to change the numbers, and we're going to do it deliberately to see what actually moves the needle. Because before we talk about impact, we have to understand scale. Now, it's important to know that nitrogen and oxygen make up 99.03% of the atmosphere. Add argon into the composition and that rises to 99.956%. Carbon dioxide is only 0.0412% or 412 parts per million. Now, that number does fluctuate slightly, anywhere between 410, 420, or even 430 parts per million. But we're still talking about second decimal levels of concentration here. And that matters because scale matters before impact. So when we talk about heat capacity is how much energy a material can store, and more specifically, how much energy can be stored per degree of temperature increase. Now, air has a heat capacity of 1003.5 joules per kilogram per degree Celsius. Now, my own independent calculation comes out to around about 1007.77 joules per kilogram per degree Celsius, and that's a 0.43% difference, which I'd argue is pretty good for government work. Now, here's the assumption that I'm making based on common climate arguments. I only change the carbon dioxide concentration, nothing else. If we increase carbon dioxide tenfold from 412 parts per million to 4,120 parts per million, the heat capacity drops by just 0.19%. If we increase carbon dioxide 100 times to 41,200 parts per million, which by and large is also now 4% of the atmosphere and already well past the harmful levels such as affecting cognitive function at 1,000 parts per million and at 5,000 parts per million causing headaches and drowsiness, 40,000 part per million is immediately medically dangerous to humans with effects such as dizziness, confusion, and potential loss of consciousness according to the USDA. Now, at 41,200 parts per million, heat capacity drops by just 2% to 987.67 joules per kilogram per degree Celsius. So what does this mean? Adding carbon dioxide reduces the air's ability to store heat, and for the same amount of energy, the temperature increases by 0.02 of a degree. So that's 0.02 degrees. Not whole degrees, not even tenths. We're talking hundredths. Now that alone should make anyone stop and ask questions. Numerically, carbon dioxide doesn't have enough influence to significantly affect atmospheric temperature via the mechanism of heat capacity. But heat capacity only tells us how much energy air can store. So let's keep going. Now, thermal conductivity describes how easily heat moves through a material. If warming occurs, energy has to pass through the atmosphere, not just sit inside it. Now, the thermal conductivity of air is between 0.024 and 0.026 watts per meter Kelvin. Now, my calculation came out to 0.02392 watts per meter Kelvin, and once again, I think that's pretty close. Now, carbon dioxide's thermal conductivity is 0.0146 watts per meter Kelvin. Now, that's lower than air, and this is important because lower conductivity means less heat actually makes it through. So when we increase carbon dioxide numerically, the thermal conductivity actually drops. If we increase carbon dioxide from 412 up to 41,200 parts per million, a factor of 100, the thermal conductivity drops to 0.02356 watts per meter Kelvin. That's a 1.5% reduction in heat transmission despite 100 times increasing carbon dioxide, which means less energy gets through the atmosphere, not more. And this is where things start to go a little bit sideways. Now, this is where we get to the stadium problem. Nitrogen and oxygen both have thermal conductivities of about 0.024 watts per meter Kelvin. Now, that makes sense considering that they make up 99% of the atmosphere. So now we have to ask the uncomfortable question: how can less than 0.05% of the atmosphere be responsible for global temperature control? Here's the analogy. Imagine a stadium with 100,000 people in it. Carbon dioxide would represent only 41 of those people, and we're blaming those 41 people for the temperature of the entire stadium. Now, forgive the expression, but that doesn't quite pass the sniff test here. So let's push this further. Let's take a column of air. Let's say it's just 1 square meter in cross section and it's 1,000 meters high with a 6.5 degree temperature difference constant. Yes, now the height here in this case is arbitrary, and I've also assumed that this column of air also maintains a uniform density. And this just shows how we use simplifications even in the most basic of calculations. And yes, this actually inflates the result. Where the column of air, as it's increased, the heat transfer would technically go down. But even then, 100 times increasing carbon dioxide on these numbers reduces heat transfer by around about 1.52%, or in this case, by about 2.38 microjoules. And when we look at the raw values themselves, we can safely say that heat transfer isn't even worth considering as the dominant heating process. Direct solar radiation is orders of magnitude more powerful, as well as instantaneous. All the same, so far every mechanism we've touched says the same thing. Temperature change is barely perceptible in terms of the energy that's actually stored, and since that thermal conduction drops, heat transfer decreases in both directions, and the effects remain negligible at part per million scales. And yet, none of this is ever discussed, not from the point of energy flows. And this is where we get to the greenhouse effect. Instead, the conversation with respect to climate change and global warming jumps straight to the greenhouse gases and the greenhouse effect. Now, the greenhouse effect itself is real, and it's one that we all know about, and again, we can easily relate to it. In short, take any enclosed system, whether it be a car, a house, or in our case, an entire planet, anything with a boundary layer between the heat source and the point of measurement, and the enclosed space will always trap heat. Now that's just basic physics. Sit in a parked car on a sunny day and you'll find out just how quickly this happens and how powerful the effect is. But here's the problem. Blaming that effect on trace gases like carbon dioxide, methane, or CFCs doesn't scale. Now here's why. A car could be 30 to 40 degrees hotter inside than it is on the outside. The greenhouse in this case is created by glass being the boundary layer between the two environments. But no one attributes that level of thermal differential or increase to 0.04% of the air being carbon dioxide inside that car. That's not just wrong, that's not even wrong. Now, methane exists at about 1.87 parts per million, but we're told it's around about 50 times more powerful than carbon dioxide. And yet, that's less than one person in the entire stadium. Even if we compensate by a factor of 50 times, that's only 9 people in the stadium. And now at 50 people being responsible for the temperature at the equivalent of around about 500 parts per million. Now, CFCs and halocarbons exist at around about 1.5 parts per billion. Now, that's the equivalent of about 12 people in a global population of 8 billion. It's okay if you're starting to get skeptical at this point based on concentrations alone. You probably should be. Now, water vapor within the atmosphere can reach concentrations of as high as 30,000 parts per million or up to 3% of the atmospheric concentration. Now, that's nearly 73 times higher than carbon dioxide. And we know beyond any doubt that water affects climate. It's an effect so well known that we call it the weather. Now, cloud cover affects nighttime temperatures. Cloud cover traps heat and clear skies release it. Humidity affects our comfort. Steam powers turbines and steam has run entire industries. Water has enormous heat capacity. We don't debate this. It's known science. And yet, it's almost never framed as part of the problem. Because just imagine how the conversation would end up if we ever talked about water vapor as a greenhouse gas or as a pollutant. Things would get very complicated and I suspect very inconvenient very fast. Now, carbon dioxide is 0.0412% of the atmosphere. Now, that's 41 people in a stadium of 100,000. But from a business perspective, and to many extents being driven by policy and regulation, industry is being forced to adjust to the point where that's like restructuring the global economy to save 4 cents in every $100. But it's not even that. Some benchmarks even use 200 parts per million of carbon either as a target level or as a geological benchmark that we need to achieve. Now, if we factor in the 200 part per million benchmark, now we're talking about 2 cents in every $100. Now, anyone pitching a business case for just a 0.02% improvement or a 0.02% profit boost or an investment with just a 0.02% return would be laughed out of the room in seconds. Think about it. A 0.02% return on $100 would take 5,000 years to pay out, unless it's framed as an existential threat. Then suddenly cost no longer matters. In 2024, I asked the question about how much energy we truly need, and the number I came up with at the time would be somewhere in the order of around about 354 terawatt hours per day, or around about 14.75 terawatts of instantaneous capacity. Now, even if we factor in a low ball target of around about $750,000 per megawatt of production, it would cost in the order of $11 trillion up front just to build that level of capacity. Now, by the time we think about capacity factors for renewables, and then triple that capacity to compensate for solar and wind that aren't producing at any one time, we're talking about over $30 trillion in capital expenditure for just a 0.02% difference. If we make that cost higher, we're talking about $40 to $50 trillion. So if carbon dioxide were truly an existential threat, surely fossil fuels would be banned outright. And yet, they're just not. Now, I'll admit at this point, some of the questions are very one-dimensional and binary. Industry doesn't have an alternative to oil and gas, particularly when it comes to heavy industries like transportation. There's too much infrastructure and industrial inertia to overcome here to simply put an end to something like oil and gas. But if the threat was as big as it's meant to be, an immediate phase-out would be the only choice on the table. Now, we did this with CFCs, phasing them out in the Montreal Protocol, ceasing production in 1996, and in developing nations by 2010. Energy-intensive industries like artificial intelligence and crypto that demand massive amounts of energy from any and every source they can get their hands on should have been regulated out whilst the direct models were still in the lab so that they'd never be allowed to scale. We wouldn't be letting those industries keep expanding, let alone making them available on a global level to a population that will adopt AI and blockchain in the same way that we adopted the internet, driving the demand for energy in only one direction. And yet, they are. Demand wouldn't be increasing, and yet it is. Now, those aren't opinions. These are observable contradictions. Now, combustion always produces water, always. For every carbon atom burned, you get one more water than carbon dioxide. Yet carbon is treated as the villain, and water gets a free pass. Now, it's funny how that works. And again, I'm only following the math, the science, and the observable trends. Now, this analysis doesn't prove that climate change is wrong. And despite everything that I've made in this video, disproving climate change isn't actually the goal. That's not the point. It shows that carbon dioxide at its current concentration doesn't have the physical leverage to move the global temperature in the way that it's claimed that it does. A 0.02 degrees Celsius effect does not justify a planetary-wide economic and industrial overhaul. Now, make no mistake, we should look for better solutions. And if industry has taught us anything, once a better solution is found, one that's commercially viable and not just a multi-step process to a second best option, industry and entire economies will make the move on their own. The one substance that does have the concentration, the heat capacity, and the observable impact is the one substance no one wants to label as a pollutant. And that's because we drink it. And once you see that, things start to smell off. But on that note, I'm going to thank you for watching, and I'll see you in the next one.